So like I explained in the previous slide, here you can draw a complete circle that gets circumscribed, or gets inscribed actually. It gets inscribed in the grid block. W frac is 1. So same view here. Covers all of the grid block. But here, when it's on the corner, then this is what the circle around the wellbore will look like, and it accounts for only 1/4 of the area, and so W frac is 1/4. Here you can draw it this way, and it accounts for only half of the area, so W frac is half. Same deal here. How about geometric factor? It's related to the geometry of the grid, and it's 0.37 here, 0.34 here, 0.35 here. They all look, delta x is very close to delta y. But when it's significantly different, then the geometric factor goes up, which is what you see here. So this is why we say the well model is able to account for both the geometry of the grid block, which is what the geofrac is doing, and geometry of the fracture. More details from the IMEX manual. There is a keyword geometry, so we can do star geometry. Then you need to specify the direction in which the well is drilled. If it's a vertical well, then we'll be looking at geometry space star K. So you will do geometry so that's star geometry, then star K for vertical well. If it's a horizontal well drilled in the I direction, star high. If it's drilled in the J direction, star J. So that's how these keywords work. Then for rad, you provide the radius of the wellbore in whatever unit you have chosen at the beginning of the input file. The geofrac, of course, is related to the geometry of the grid. And we point out here that if you're using either of these two keywords, then we wouldn't be using the geometry keyword. And those will actually calculate the effective wellbore radius using these equations, depending on the direction of the well. So if the well is a vertical well, so it's in the K direction, so we'll be using star K here. Then the two permeabilities that will control the flow, because the well is vertical, will be Kx, and the one in this direction, Ky. So coming from behind the screen towards us, the Kz will not contribute to the flow because the well is moving down in the Kz direction. So that's why you only see Ky and Kx here. If the well is horizontal and parallel to the J direction, so the J direction is the direction of Y. So this way, then Ky will not contribute. It's going to be Kx and then Kz. So you see only Kz and Kx here. And similar thing goes for the well parallel to the I direction. So X, permeability in the X direction will not contribute. It will be only Ky, right, and Kz, which is what you see here. So those are the corresponding effective or the corresponding equations for the effective wellbore radii. I already explained the well frac, and it's a real number. Oh, sorry, we're talking about skin now. So the skin is a real number that specifies the skin factor, which you all are familiar with from production engineering. And we basically bring in skin. And I already showed the equation for that previously. It gets added to the natural logarithm of the effective wellbore radius divided by the actual wellbore radius. And in that case, when you're using this equation for the flow rate into the wellbore, we'll need to provide the effective wellbore radius calculated using this equation, provide the wellbore radius, and provide the perpendicular area towards the wellbore, which for a vertical well will be delta x times delta y, right? That's the perpendicular area to the wellbore. So this equation right here, together with these parameters, apply to the geometry keyword. So that's how you get effective radius when you're using the geometry keyword. But when you're using GOA or KHA keywords, then we'll calculate effective wellbore radius from Peaceman as shown here, depending on the direction of the well. And again, you got the reference paper for that well treatment. In CMG, you can also set the productivity index for the well. And so the simulator will honor the productivity index you type into the data file. Why is this important? If you perform a well test and then from the well test you calculate the productivity index, you can constrain the simulator to honor that productivity index. And you can have productivity index for all the different phases. You can also have multipliers, so it's going to multiply whatever the calculated productivity index is in the simulator by whatever value you provide. Multiply all of the productivity indices or the productivity indices for all of the phases, whereas mult O will multiply the productivity index for the oil phase by whatever factor you provide. So that's what the SetPI model does. And like I said, provide oil, water, gas keywords to choose whichever phase you want to multiply. And these will be the corresponding units depending on whatever unit you already selected at the beginning of the input file. More on IMX well treatment. Productivity index you already know is related to Q is J delta P, right, from production engineering. So J is Q over delta P. In the same vein, the well index or the well productivity index is the ratio of the flow rate, production rate, to the pressure drawdown, which is what you see here. And so we can have it for the different phases, which is why we can have set productivity index keyword for any of those three phases. You can also have it for the total production. And the main thing is to be able to honor well index calculated from well testing, like I said earlier. It basically scales whatever productivity index is calculated from the simulator to match whatever value you provide. This is an example of an input data file for CMG IMX. So here we specified field units. So the productivity index you provide has to be in field units, and I showed the corresponding units for that. Here we're using the geometry stack K. So in what direction is the well? It's a vertical well, right? From top to bottom. This is the radius of the wellbore in field units. So that would be in feet. Geometric factor, the well fraction. So you can draw a complete circle within the grid block. Basically, the well is centered. Basically, it means that the well is centered close to the centroid of the grid block. So whether or not even if the well is like this and it's centered in it, well frac will be 1. But if it's X-centered or placed on the corner of a wellbore, then well frac will be 0.25. Skin, we're going to account for formation damage. Then we have your date indicating the onset of the simulation. You can set PI and provide a multiplier for the oil phase. So for these two grid blocks, for these two grid blocks, it could also correspond to the 2 layers. Multiply the productivity index by 1. That's what this does. In this other case, for everything, all the grid blocks in the domain, or better still, for all the wells in the domain, multiply the productivity index by 2.3. Here, for the first 2 wells in the domain, multiply the productivity index for the oil phase by 1, so leave it unchanged. And by the way, how do I know this 1 to 2 was for the wells and not for the grid blocks? It corresponds to these. It's a keyword that applies to the well and not the grid block. How much time do we have? Okay, so I'm going to pause the video here and continue in the next video.